Hi, my name is Horacio Silva Saravia, and today I'm going to talk about our transactions paper, Adaptive Coordination of Damping Controllers for Enhanced Power System Stability. The motivation for this work can be explained by trying to answer two simple questions. The first one is, how can we measure oscillation damping performance in power systems with multiple critically damped oscillations, which is something that can become a real problem as we move towards systems with higher penetration of renewable energy. We propose an answer to this question, and that is by using a concept that we call total action. The total action is an analytical expression that naturally weights the dependency of each electromechanical mode in the system, being a function of system parameters such as inertia, but also a function of the disturbances. The second question that we're trying to answer is how to control such systems with multiple critical modes. Most of the answers that we found in different articles involve optimization-based approaches, which may work great for a given configuration or a worst-case disturbance associated with some probability distribution, but in general do not work with, in an optimal sense, looking at real-time conditions. Actually, most approaches completely ignore the fact that the control performance strongly depends on location of the disturbance, which at the same time means that performance depends on what are the modes that are excited for a given disturbance. Here is where our proposed solution provides additional value. In this paper, we propose a disturbance adaptive control that coordinates damping controllers to ensure optimal performance in the sense of the total action. This coordination is implemented through a combination of a centralized controller and the traditional local controllers in damping actuators. The centralized controller senses the disturbance and with that performs a sensitivity analysis to determine what are the changes in the current set of damping controllers that have a better impact on decreasing the total action as a measure of performance. Once this is determined, the centralized controller sends out switching signals to enable or disable the local damping controllers. Note that these switching signals do not turn off actuators, but only the damping control loop in those actuators. The actuators in this paper are electronically interfaced resources such as batteries and wind farms. We tested the performance of the adaptive coordination control in a reduced model of the Western North American power grid, and the results show that by adaptively switching on and off sensitive damping controllers for different disturbances, we can adaptively minimize the total action and drive the oscillation energy quickly to zero, in many cases much faster than the case without coordination. Additionally, we tested the performance of the system under real-world conditions using large communication delays in which the system still showed an improved performance. Finally, I want to leave you with two key messages. One is that oscillation energy and total action can be used to measure dynamic performance in complex systems. And also, the use of a disturbance adaptive coordination approach can improve the overall dynamic performance of the power system. Thank you.